Bismillahirrahmanirrahim. Assalamu alaikum students. Welcome to our 31st lecture of MTH108 Business Math 1. Today we will continue with our chapter 14, which is about probability distributions. Let us recall what we have studied in our previous lecture. In our previous lecture we have studied the random variables and the types of random variables as the discrete and continuous random variables. Then we have seen the frequency distributions and how we can find the relative frequency. Then we have defined the probability distributions, and these are actually the relative frequency of the random variable. Some properties of the probability distribution which are same as the properties of a probability function. And how we can define our probability distributions by using a histogram. We have defined briefly what do we mean by a histogram. It is nothing but a bar graph, and in this we draw the rectangles and what does each rectangle mean. Then continuing further, we have studied some measures of central tendency, that is the measures to determine the central location of our data set point. In these measures we have studied the mean, the median and the mode, and it depends on the situation, on the type of our data set, that what type of measure is required to calculate. In case of mode, we have seen that it is the simplest and easiest measure to calculate. We don't need a calculator, and with this type of measure we can calculate the qualitative data as well as the quantitative data, as we have seen in the example. And in the end of our previous lecture we have seen the formula for the mean of discrete probability distribution. Today we will continue our chapter with the topic of variation, and then we will see the binomial probability distribution. That is a special type of probability distribution known as the binomial probability distribution. Now in our previous lecture we have studied the measures of central tendency, that is the measures which determine the central location of our data set point, and the main one was the mean of our data set point. That is, mean provides a measure of central location of the data. But this is only one attribute of a data set. To describe the data more fully, it is useful to look at other attributes. For example, we may also be interested in considering that how wide our data is, or to discuss the spread or variability in the data. So what do we mean by this spread or variability in the data? Let us consider two probability distributions which are given in the following table. As we have our random variable x1 with the values as 49, 50, 51, and the probabilities with respect to this random variable are given as 0.05, 0.9 and 0.05. We consider one more random variable x2 having the possible outcomes as 0, 50 and 100, and the respective probabilities as the same as for the random variable x1. So we have two probability distributions for two random variables x1 and x2, and if we look at these values of our random variables, both of these distributions have the same mean, that is, both have the same mean, mu is equals to 50. But the variation in the values of the two random variables is quite different. That is, in the first case the values are very close to the mean, and in the second case the values are far away from the mean value 50. And in this case, luckily the mean value also belongs to the possible outcome or the one value of our random variable. So to measure our data set in terms of mean is not the only information we are interested in. Both the probability distributions have the same mean, but the values from the mean are much far or much closer in one case and in the second case. So we are interested in the variability that exists within the data set. And to describe the variability that exists within the data set, we use a measure of variation. And one way to finding the variation between the points of a data set is nothing but noting the extreme of the variations. That is, the range for a data set is the difference between the largest and the smallest value. For example, if we consider the example of our last lecture, that is the scores of players in a game, they were defined as 72, 76, 78, 80 and 140. So if we want to find the range of these values of the data set, then the largest value is 140 and the smallest value is 72. So the range of this data set, that is the extremes of variations, will be the difference between the largest value to the smallest value, that is 140 minus 72, which is equals to 68. So this is the range of our data set, and we have found the extremes of the variations. But we ask ourselves that is this information enough to know the variation of our data set? No, this information is not sufficient to find the variation, because if we look at our data set, the first 4 values are very close to each other and the last value is much higher than the rest of the values. So this range or extreme of our data set also does not provide enough information about the variability, that how far our data is spread. So the range in the previous example shows that there is much variability in the scores, but if we look carefully at the data points, we observe that the first 4 scores are much close to each other and the last score has large variation from the rest of them. Thus we conclude that range of a data set can be easily calculated and easy to understand, that is, we can interpret from obtaining the range, but this does not give much information about the data values which lie between the extremes. That is, how close they are to each other, how far they are from each other, and so on. So an important observation in the measure of variation is that it should be small when the data points are close to the mean and large when they are far from the mean. So we think of another way of measuring the variation between the data set points by looking at the above mentioned observation, that is, by finding the distance of each data point from the mean. So given a sample data of n items, that is x1, x2 and so on up to xn, and the mean of this data set is mu, then the distances of the n data points from the mean would be represented by x1 minus x bar or x1 minus mu, x2 minus x bar, x3 minus x bar, and so on up to xn minus x bar. So these values represent the distance of n data points from the mean, and these differences are referred to as deviations from the mean. That is, each data point x1 is deviated how much from the mean. Simply the data set point x2 is deviated from the mean, whatever the value of the difference is, and so on. So adding these deviations and dividing by n will give the average deviation from the mean. That is, if we are adding all these, x1 minus x bar plus x2 minus x bar plus so on up to xn minus x bar, and dividing all of them by n, this will give us the average deviation from the mean. But unfortunately this sum gives us 0. What do we mean by 0? That this sum in the numerator will be equals to 0, which means that sum of all positive deviations from the mean is equals to sum of all the negative deviations from the mean. So, sum of all these positive deviations from the mean is equals to sum of all the negative deviations, and in the numerator we will obtain 0, which means that the average deviation from the mean is always equals to 0. So this method is also not applicable to know the variability of our data set points, that is how far they are from the mean or how close they are from the mean or how close they are to each other. Then for this purpose we define one thing called as the variance, which we say that each individual deviation is a measure of variation for that particular data item. That is, we know that the difference of the data set point x1 from the mean is nothing but the variation for this particular data item x1. So average deviation does not give us anything. What we can do is we can square all of them, that is squaring each individual deviation, adding all of them and then dividing by n gives us the mean of the squares of deviations, which is called as the variance. And how we define the variance? That if a data set point or if a data set consists of n items x1, x2 up to xn, and the mean of this set is given by, let's say, x bar, then the variance for the data set is defined as capital VAR, abbreviation for the variance, defined as squaring each individual deviation, that is x1 minus x bar square, x2 minus x bar square, and so on up to xn minus x bar square, adding all of them. Okay, so we are adding all of them, dividing by n. Dividing all this sum by n gives us the mean of the squares of deviations, and it is called as the variance. So one way to find the variability of our data set is to find the variance. That is, instead of taking the average deviation from the mean, which is always equals to 0, and from there we get no information, we square the individual deviations, add all of them and divide them by the total number of data items n. But it has been observed that squaring the deviations from the mean does not accurately reflect the actual magnitude of variation in the data set. So how we can improve this? We can take the square root of the variation to variance to correct this. And this measure of variation is known as the standard deviation, denoted by the Greek symbol sigma. And sigma is defined as, what we are saying, we may take the square root, taking the square root of our variance, that is the square root of all these squares added up, xn minus x bar squares divided by n, and whole taken as the under root. Okay. Or we can write this sum inside the square root in the summation form as the summation of these data points xi, difference with the mean, square of all of them, where I is varying from 1 to n, divided by n, and taking the under root. So standard deviation, which is nothing but the square root of our variance, is the most accurate measure which determines us the variation of our data set points from the mean. We can also write our variance formula in the form of summation form, as this will be equals to summation xi minus x bar square divided by n, where the summation varying from 1 to n. So by using the variance, we have defined our measure of variation known as the standard deviation, and by taking the square root of our variance, this sigma or the standard deviation is the commonly used measure of variation for a set of random numbers. Okay, now we come to an example. Suppose we consider the scores of a student taken 5 exams during a college math course. This is the example which we have discussed in our previous lecture as well. And if we recall from our previous lecture, the scores were 78, 96, 82, 72 and 92. These were the scores a student has taken in 5 exams during a college math course, and the mean of these scores was, we can calculate the mean simply by adding all the data points, dividing by the total number of points, because here we are only provided with the data points. We don't know about the relative frequency or the probability distribution. So we will use the simplest formula of finding the mean, that is adding all the data points divided by the total number, which is 5, and we obtain the mean as 84. Okay, we have said that the average deviation from the mean is always equals to 0. Let us see in this example that what will be the average deviation. The average deviation was the difference of each data point from the mean and adding all them divided by the total number of data points, that is 78 minus 84 plus 96 minus 84 plus 82 minus the mean plus 72 minus the mean plus 92 minus the mean, all divided by 5, and we obtain as minus 6 plus 12 minus 2 minus 12 plus 8 divided by 5, which is equals to 0 by 5 as 0. So we can clearly see that average deviation does not give us any information about the variation of the data from the mean. And now we calculate the standard deviation for these data points, and we already don't know the mean. For this, first we have to calculate the variance, that is variance will be the square of these numbers, that is minus 6 square plus 12 square plus minus 2 square. Okay, and this all divided by 5 we obtain after calculation as 78.4, and the standard deviation is the under root of our variance, that is under root of 78.4, which is 8.85. So this tells us that each point is spread at 8.85 units from the mean. So with the help of data points, we can easily calculate the standard deviation first by calculating their respective mean. Now we define the standard deviation for the discrete probability distribution. Since we are more focusing on probability distributions in this chapter, the relationships involving standard deviation and probability distributions can be useful in reaching conclusions about a data set. For this, if we are given a discrete random variable x, which can assume n values, x1, x2 up to xn, having respective probabilities of occurrence p1, p2, so on up to pn, then the standard deviation also abbreviated as SD of the random variable with mean mu is defined as how? Do we have to divide it by n? No, in this case we will simply take the squares of the variation from the mean and multiplying the respective probabilities of occurrence, that is x2 minus mu square into the respective probability p2 and so on up to xn minus mu square into the respective probability pn, but the under root remains there. If we look at this formula without the under root and without the squares, we have calculated the mean when we know the probability distributions, that is the respective data item into a data item into the respective probability plus a data item into the respective probability and so on. So using that formula we can also obtain the standard deviation, and we can write this formula in the summation form as xi minus mu square into the respective probability of occurrence pi, where the summation is varying from 1 to n, and whole to the whole under root or whole to the power 1 by 2. Now we come back to our example, that is in which we have discussed two random variables and they were given with their respective probabilities. The first random variable having values were 49, 50, 51 with the respective probabilities of occurrence as 0.05, 0.9, 0.05. The second random variable has the values 0, 50, 100 with the respective probabilities same as for the random variable x1, that is 0.05, 0.9, 0.05, and we know that the mean in both the cases is 50. So the standard deviation sigma 1 for the random variable x1 will be equals to 49 minus 50 square into 0.05 plus 50 minus 50 square into 0.9 plus 51 minus 50 square into 0.05 whole to the power 1 by 2 or whole under root, which is equals to 0.05 plus 0 plus 0.05 1 by 2 0.1 under root, which is equals to 0.312, and the standard deviation for our random variable x2, this will be equals to 0 minus 50 square into 0.05 plus 50 minus 50 square into the respective probability plus 100 minus 50 into the respective probability whole to the power 1 by 2, which is equals to 50 square, that is 250 into 0.05 plus 0 plus 250 into 0.05 whole to the power 1 by 2, which is equals to 125 plus 125 under root, and 250 under root is 15.81. So the standard deviation sigma 1 for our random variable x1 tells us that the values are very close to the mean. All the values in the data set are very close to the mean. And the standard deviation for our random variable x2 tells us that the values are far from the mean. That is, the smaller the standard deviation means that the values are very close to each other. The larger the standard deviation, the values are far from the mean. We consider one more example of the blood bank with the random variables and relative frequencies given as the possibilities of the random variables, where the random variable was the units removed x, and the relative frequency was given, that is, the relative frequency was calculated, where when 0 units are removed happened in 2 out of 80 days, and the relative frequency was 0.025. When 1 unit was removed happened in 6 out of 80 days, and the relative frequency was 0.075. And now I simply write the units removed and their relative frequencies. That is, when 2 units are removed, the relative frequency was 0.1, and same was for when 3 units were removed. When 4 units were removed, the relative frequency was this one in the case of 5, in the case of 6, in the case of 7, and in the case of 8. So, in order to find the standard deviation, we will simply, first we have to calculate the mean. The mean will be, mu will be equals to adding all these data points and dividing by n, because we have odd total data points. But we have seen that in the case of median, that when we have odd number of data points, then our median is actually the middle number is actually the mean. So in this case, mean is equals to 4, and our standard deviation will be equals to 0 minus 4 square into the respective probability plus 1 minus 4 square into the respective probability, which is 0.075, and so on, plus up to 8 minus 4 square into the respective probability whole power 1 by 2 or under root. And solving this, we obtained 0.4 plus 0.675 plus 0.4 plus 0.1 plus 0. 0 is the term when we are calculating 4 minus 4 square into the respective probability 0.125. Okay, then for the case of 5 units removed, for the case of 6 units removed, and 1 by 2, all of these values with sum of all these values with under root, we obtained 4.8 under root, which is 2.19. which means that the data points are 2.19 units from the mean. With this, we have some practice questions from the section 14.2, which basically deals with the measures of central tendency, that is mean, median, mode, and the measures of variation, that is the standard deviation. Now we start our second topic of today's lecture, which is about the binomial probability distribution. Now the binomial probability distribution deals with the discrete random variables. In our previous lecture, when we have defined the random variables, we have classified them in two types, that either they are discrete or they are continuous. And we have seen many examples of discrete random variables. Up to now, the formulas we have defined are all for the discrete random variables. Many random processes are characterized by trials in which there are just two mutually exclusive outcomes, that is the independent trials. Okay, we consider the independent trials, that is the type of trials in which the possible outcomes are mutually exclusive to each other. We are not considering mutually exclusive trials. You may get confused with the mutually exclusive trials with the independent trials, but we are considering independent trials, that is the trials in which the outcome of one trial does not affect the outcome of any other trial. Okay, but in this type of independent trials, we are further considering that the outcomes can be only of two types, that is there are only two possibilities of the outcomes, and these two possibilities have nothing in common. For example, if we toss a coin, then no matter how many times we perform this experiment, each trial does not affect the outcome of the next trial or the outcome of the previous trial, so it is an independent trial. And in each case we have only two possibilities of the outcomes, either we will obtain a head or we will obtain a tail, and both of these are totally different from each other, that is they are mutually exclusive. So we are considering random processes in which, but in particular we are considering independent trials in which the possibility of outcomes are only two, and these outcomes are mutually exclusive to each other. For example, manufactured parts, they are maybe referred to as acceptable or defective, and if one part is manufactured as defective, it has no effect on the next part. The next part may be defective or may be acceptable. So these type of outcomes, possible outcomes, when we have only two and they are mutually exclusive to each other, either the manufactured part will be acceptable or it will be defective. For example, patients arriving at an emergency room classified as male or female, then it is also an example of an independent trial, and the possible outcomes are mutually exclusive to each other. For example, survey questionnaires mailed to potential respondents as returned or not returned. Again, this is an example of independent trial, and if one has returned the questionnaires, then it does not affect the possible outcome of the other person. For example, questions on a multiple choice as correct or incorrect, if the answer of the first multiple choice question is correct, it does not affect the answer of the second question in the multiple choice, which means that it is an example of an independent trial, and we have only two possibilities as our outcomes, either the answer is correct or incorrect, which means that the possible outcomes are totally different from each other, or the complement of each other. Then frequently the possible outcomes in these situations are characterized as successful or unsuccessful. Since we have only two possibilities of outcomes, either the answer on a multiple choice question is correct or incorrect. Then if the answer is correct, we may classify it as a successful outcome. If the answer is incorrect, we may classify it as an unsuccessful outcome. So we may classify our outcomes one as successful and the other as unsuccessful depending on our situation. So these type of experiments which are independent and the possibility of outcomes are only two, which are mutually exclusive to each other, are the examples of Bernoulli process. And the Bernoulli process have the following properties. That is, if there are n independent trials, each of which has two possible outcomes, success or failure, or successful or unsuccessful, the probability of a success P remains fixed for each trial. For example, if we toss a coin once, then the probability, if we define success as obtaining a head, then the probability of obtaining a head in first trial is 1/2. We flip a coin second time, the probability of obtaining a head again is 1/2. So the probability of success remains fixed for each trial, and we denote it by small p. Similarly, the probability of failure, that is we denote it by small q, is also fixed for each trial, and since the two outcomes are mutually exclusive to each other, that is the sum of the probabilities of both the outcomes will be 1. So the probability of failure will be nothing but 1 minus the probability of success. The random variable x is the total number of successes in n trials. That is, suppose we have flipped a coin 3 times and we define our random variable x, the success, as when we obtain head, and we have obtained head when we have flipped the coin 2 times, which means that the random variable will have the numbers 0, 1 and 2, that is the number of successes in n trials. For example, we assume that a single die is rolled 25 times and we define our successful outcome as the occurrence of 6 in a roll of the die. So this is our random variable, and this is clearly an example of a Bernoulli process because each trial is an independent trial and the outcomes will be either a success or a failure. Either we will obtain a 6 or we will not obtain a 6, which means that the probability of success for each trial is 1/6. That is, in each time we have rolled our die, the probability of obtaining 6 is 1/6. And since this is a Bernoulli process, the probability for obtaining a success in each trial will be 1/6, which is denoted by small p. So the probability of failure, that is the small q, for each trial will be 1 minus p, which is 1 minus 1/6, which is 5/6. So in each trial, the probability that we will not obtain 6 is 5/6. And we can see that these successive roll of die 25 times or even 100 times are independent trials. And we define our random variable x as x is the number of successes in n trials, that is the number of times a 6 occurs in 25 rolls. So this will be our random variable, that is the number of successes in n trials. The trials here are 25 and the number of successes when we have obtained 6 when we have rolled our die. So the number of times a 6 occurs in 25 rolls. Let us consider one more example similar to this one. We assume that 100 parts will be selected from a manufacturing process which is to be judged to produce defective parts at random with probability of 0.05. So Since the process of producing defective parts or acceptable parts is independent, producing or resulting in defective parts is independent. So it is an example of a Bernoulli process. Okay, we define our random variable x as the number of non-defective or acceptable parts produced in 100 trials. Okay, so this will be our random variable x, and our p will be equals to, we don't know, but from the data we clearly know that the defective parts at random with probability of 0.05. So q, that is the probability that we will obtain a defective part or a defective part is produced, is 0.05. So the probability of success, that is an acceptable part is produced, is 1 minus q, which is 1 minus 0.05, which is equals to 0.95. And this is the successful outcome. Now we define the Bernoulli distribution. We consider a student who is taking a true-false quiz consisting of 5 questions, and we assume that the probability of answering any one of the questions correctly is 0.8. Okay, and we are interested in knowing the probability that a student will answer exactly 4 questions correctly. Now this is again a Bernoulli process, because if a student has answered first question as true, then it does not affect on the answer of the second question. How we will find the answer in this case? If in this case we know that the probability of success is equals to 0.8, that is answering any one of the questions correctly is 0.8. So the probability of failure will be equals to 0.2. And what is our random variable x here is, that is the number of correct answers in 5 questions. So this is our random variable. So the probability that we obtain a success, that a student has answered a question correctly, is 0.8, and the probability that probability of failure, that the answer of the student is false, is 0.2. And we want to find the probability that a student will answer exactly 4 questions correctly. For this we need different combinations, that is the different combinations of answering 4 questions correctly and 1 incorrectly. Then S, if we define S as our success, that is the answer provided is correct, and we define capital F as our failure, that is the answer provided is incorrect, then the possible combinations that a student has answered exactly 4 questions correct will be, if he has answered first question correct, second, third, fourth, and the answer of the 5th question as incorrect. Similarly, if he has answered first 3 questions correct, the 4th one incorrect, and the 5th one again correct. Similarly, if he has answered first 2 questions as correct, the middle one incorrect, and the last 2 again as correct. Okay, other possible combination will be if he has answered first question correct, second false, and the last 3 as correct. And we have one more possibility, that he has answered first question incorrect and all the 4 questions, rest of the 4 as first question incorrect and all the rest of the 4 as correct. For example, we consider the last case, that is when he has answered the first question incorrect and the rest of the 4 as correct. Then, since we are considering the independent trials, so one is an independent trial, so the probability of this one will be equals to the joint probability, that is the joint probability of all the events, which is S2 intersection S3 intersection S4 intersection S5, the joint probability of all the events. And since the events are, the possible outcomes are mutually exclusive and we have an independent trial, so this will be the product of the probabilities of all the events. That is, the probability when the first question is incorrect is 0.2, for the second one 0.8, for the third one again 0.8, for the fourth one correct, and the 5th one correct is 0.8, which is equals to 0.2 into 0.8 to the power 4, which is 0.08192. Similarly, if we call this combination as combination 2, then the probability of our combination 2 will be again the probability of the product of the probability of all the events, that is by using the joint probability of S1 intersection S2 intersection S3 intersection S4 intersection S5, which is equals to 0.8 to the power 4 into 0.2, which is the same as in the case of our first combination. Similarly, if we call this as our third combination, this as fourth and this one as 5th, then the probability for our third combination is same as the probability for our fourth combination and same as for the 5th combination. Because in each of these, what we have only one false, so they are independent trials with the mutually exclusive outcomes. By using the definition of joint probability, in each case we have only one false, which means that the probability of this will be 0.2 and all 4 of them will be the probabilities of success, that is 0.8 into 4. Only their order of multiplication will be different and all of these have the same probabilities. So the probability will be actually of the random variable when we have exactly 4 answers correct will be equals to the number of different ways in which 4 questions can be answered correctly into what? Into the probability of answering 4 out of 5 questions correctly. Okay, just the product of these two. Now how many different ways we can obtain 4 questions answer correct is 5 ways, and the probabilities in each case which we have calculated as 0.08192, and calculating is we obtained 0.4096. Now alternatively, to find the number of ways in which 4 questions can be answered correctly, that is, since the order does not matter here, the arrangement of the questions or the answers obtained does not matter. We are only interested in knowing that 4 answers are correct and 1 is false. So we can also use the combination, because the order does not matter here. So we can use combination as, combination is NCR, where here N is equals to 5 and R is equals to 4. That is 4 questions answered correctly out of 5. So the different ways will be equals to 5 factorial divided by 4 factorial into 5 minus 4, which is 1 factorial, which is 5 into 4 factorial divided by 4, which is equals to 5. So either we will use a combination if our data set is large, or we can write each of the possible combinations separately to know the number of ways. If we are not interested in writing the number of ways, we will simply use the combination, and we will find our probability for that particular random variable. So in this case, again by using the combination, 5 into the probability of answering 4 questions out of 5 correctly is this. Now summarizing all these, now we define our binomial probability distribution as the binomial probability distribution which is used to represent experiments which are Bernoulli process, that is experiments with discrete random variable, and further we have independent trials, and the possible outcomes are only 2, either the success or failure, that is the possible outcomes are mutually exclusive to each other. So if we are given a Bernoulli process where the probability of success in any trials equals P and the probability of failure equals Q, the same notations which we have seen in the properties of Bernoulli process, then the probability of K successes in N trials is denoted as P K N, as N C K, that is the combination number of ways in which we can obtain into the probabilities of product of the probabilities of success up to K times, and the product of the probabilities of failure up to N minus K times. So PKN is equals to this combination Nk, P to the power K, that is the product of the probabilities of success. We have K times success in N trials, that is P to the power K, into the product of the probabilities of failure is N minus K. In our previous example, the probability of failure was only 1, so it was equals to N minus 5 minus 4, which is equals to 1, and the product of the probabilities of success, it was 4 times, so 0.8 to the power 4 and 0.2 to the power 5 minus 4, and the combination in front of them, that is this number of ways. So this is the general formula for the binomial probability distribution. That is the number of ways or the combination into the product of the probabilities up to the success times, if the success is k, p to the power k, into the product of the probabilities of failure up to n minus k times. And now we consider an example. We consider our same quiz example. So the possible outcomes for the quiz are 0, 1, 2, 3, 4 and 5. That is either no question is answer correct, only one question is answer correct, 2 questions, 3, 4 and 5, that is all the questions are answered correct. And our random variable is the number of questions answered correct, provided we have 5 total questions. So the probability of 0 success, that is when capital X is equals to 0, will be the number of ways, that is 5 factorial divided by 0 factorial into 5 minus 0 is 5 factorial, in which we can write, and the probability of answering 0 questions correct out of 5 questions will be equals to, the probability of answering the correct is 0 and the probability of answer of the failure is 5. So by knowing the formula, we can easily calculate the binomial probability distribution. From here we obtain 5 and 0.2 to the power 5 is 0.00032, which is equals to, from over here we obtain 5 by 5, which is 10.000032. Similarly, the probability of 1 success, that is the student has answered only 1 question correct from the 5 questions, will be 5 factorial divided by 1 factorial into 4 factorial into 0.8 into 0.2 to the power 4, which is equals to 5 into 0.00128, which is equals to 0.0064. Okay. Now the probability of 2 success, that is a student has answered 2 questions correct out of 5 is 5 factorial divided by 2 into 3 factorial into 0.8 to the power 2 and 0.2 to the power 3, which is equals to 10 into 0.00512, which is equals to 0.0512. The probability of 3 success will be 5 divided by 3 into 2, 0.8 to the power 3 and 0.2 square will be 10 into 0.02, which is equals to 0.2048. The probability of 4 success we have already calculated. Now the probability of 5 success, that is, or probability when our random variable is equals to 5, that is a student has answered all the questions correct, will be equals to 5 divided by 0 factorial into 5 factorial into 0.8 to the power 5, which is equals to 0.3276. And from all these we observe that since all outcomes of a random variable are mutually exclusive and as well collectively exhaustive, the sum of all the probabilities will be equals to 1. That is the sum when we have 5 success plus the sum when we have 4 success plus the sum when we have 3 success plus 2 plus 1 and plus 0. The sum of all these probabilities is equals to 1 because all the outcomes are mutually exclusive as well as collectively exhaustive. And we can represent this with the help of our histogram. That is, if our x-axis represents the number of success or the correct answers, and our y-axis represents our probability of correct answers, that is probability of correct answers. We start with 0.1, 0.2, 0.3 and 0.4, and here we have our number of success. Then the probability that no answer is correct was very low, it was 0.00032. The probability that one answer is correct was 0.006. The probability that two answers are correct was 0.05. The probability that three answers are correct was 0.2. Of four answers correct was 0.4. Okay, and of five answers correct was 0.32. And the sum of all these probabilities is equals to 1. So in order to find the binomial probability distribution of a Bernoulli process, where our random variable is a discrete random variable, we should know the number of ways by using the combination, the probability of success, and the number of times the success has occurred in n trials, and the probability of failure. Now we define two more things related to this binomial probability distribution as the mean of a binomial distribution and the standard deviation. Now the mean of this mean value mu for a binomial distribution is determined by the equation mu is equals to np, where n is the number of trials and p is the probability of success. So the mean number of success in a Bernoulli process equals the product of total number of trials, that is the product of total number of trials n to the probability of success p. For example, if we have a binomial distribution about the number of heads occurring in 500 flips of a fair coin, then the mean in this case will be equals to n into p, where n is equals to 500 and the probability of obtaining a head in each trial is equals to 1/2. So the mean in this case will be equals to 500 into 1/2 is 250. Let us consider one more example of this students taking a true-false quiz involving 5 questions. Then the probability of obtaining a success, probability of success p was 0.8, total number of trials were 5, so the mean in this case will be equals to 5 into 0.8, which is equals to 4. Let's say if the questions are equals to 36 with the same probability of success, that is 0.8, then the mean in this case will be number of trials into the probability of success, which is equals to 28.8. Similarly, by knowing the number of trials, the probability of success and the probability of failure, we can define the standard deviation of a binomial distribution as the standard deviation of a binomial probability distribution is determined by the equation sigma is equals to the product of n, p, q under root, where n is the number of trials, p is the probability of success, and q is the probability of failure, and with under root. For example, in the case of true-false quiz, the probability of success was 0.8, that is the probability of answering questions correct. The probability of failure was 0.2, and the number of trials or the total number of questions were 5. So the standard deviation in this case will be equals to the product of all three under root, which is equals to 0.8. So by knowing the number of trials, the probability of success and the probability of failure, we can find the standard deviation of a binomial distribution and the mean of a binomial distribution. Then we have some practice questions from section 14.3, and with this we end our today's lecture. But let us revise what we have studied today. Today we have studied about by knowing the ways in which we can find the variation of our data set. First, we have tried the extremes of the variations by finding the range of our data set. But then we have seen that this does not give us any information about the variation of our data set. Then we have tried the average deviations from the mean, first by calculating the deviations from the mean. And we have seen that these are nothing but a zero value in any case. Then further defining our concept, we have defined the variance, and since we have seen that variance also does not give the accurate information, by taking the under root of the variance we have defined the standard deviation, which tells us precisely about the variation of the values from the mean. Then we have defined the formula for the standard deviation for discrete probability distribution. Then we have seen what do we mean by the Bernoulli process with some examples, and what are the characteristics of Bernoulli process. After this, we have defined our binomial probability distributions first with the help of the example, and then we have defined our general formula and the histogram to see clearly that what do we mean by this binomial probability distribution. That is, the sum of all the probability distributions is equals to 1, because all the outcomes in our random variable are mutually exclusive and collectively exhaustive. Then the formulas to find the mean of a binomial distribution and the standard deviation of a binomial probability distribution. With this we end our today's lecture, and in our next lecture we will study about the normal probability distribution. Allah Hafiz students.